The potential of orbital assembly for large space structures is transforming how humanity envisions the construction of future space infrastructure. With the growing interest in long-term space habitation, deep space exploration, large-scale observatories, and space-based energy generation, assembling large structures in orbit has become a critical enabling technology. Traditionally, spacecraft and satellites have been designed to fit within the volume and payload limits of launch vehicles, resulting in design constraints that limit scalability. By assembling components in orbit, engineers and space agencies can bypass these constraints and build structures far larger and more complex than those limited by terrestrial launch systems. Orbital assembly involves the construction, expansion, and integration of modular components once they have been delivered to space, typically using robotic systems or human intervention on space stations or future orbital platforms. This concept unlocks new possibilities for modular design, maintenance, scalability, and adaptability. Large-scale structures such as kilometer-wide solar arrays, multi-module habitats, deep space fuel depots, and next-generation space telescopes become feasible once the process of building them in space is mastered. The International Space Station, ISS, serves as the most prominent existing example of orbital assembly. It is a complex structure that was constructed over multiple missions by various international partners. The lessons learned from assembling the ISS regarding docking, alignment, modular integration, and astronaut involvement continue to guide the development of new orbital assembly strategies. Robotic systems are at the forefront of orbital assembly. These systems use precise control mechanisms and advanced sensors to manipulate modules, connect components, and conduct welding or fastening operations in the harsh environment of space. Robotic arms like Canadarm2 used on the ISS have shown that space-based manipulation is not only possible but highly effective. Upcoming missions are developing even more sophisticated robotic platforms capable of autonomous or semi-autonomous assembly. NASA's OSAM-1, On-Orbit Servicing, Assembly, and Manufacturing mission represents a major milestone in robotic construction. It aims to demonstrate satellite servicing and the autonomous assembly of large truss structures in orbit, utilizing robotic arms and precise guidance systems. This mission will validate technologies essential for building and maintaining large space infrastructures, such as space telescopes or antennas that require precision alignment and stabilization. The modular design of space structures is central to the feasibility of orbital assembly. Modules can be built on Earth and launched separately, then assembled like a puzzle in orbit. This approach spreads risk, cost, and development time over multiple missions and contractors. For instance, a modular space station could begin with a core life support module and gradually expand to include laboratories, storage, habitation units, and even artificial gravity rings. The ability to add, replace, or upgrade modules enables long-term use and evolution of the structure over decades. Moreover, the modular approach allows for redundancy and compartmentalization, which are crucial for safety in human-rated systems. Orbital assembly is also closely tied to the development of in-space manufacturing. Instead of launching every component from Earth, future missions could produce structural elements directly in space using 3D printing and additive manufacturing techniques. This would drastically reduce launch mass and costs while allowing the creation of optimized, lightweight, and complex geometries tailored for microgravity environments. Companies like Made in Space have already demonstrated 3D printing on the ISS, and future plans include printing large trusses, beams, and support structures directly in orbit. Combining in-space manufacturing with assembly enables flexible and on-demand construction of habitats, antennas, solar arrays, and structural frames. The construction of large space telescopes is one of the most promising applications for orbital assembly. Telescopes like the James Webb Space Telescope push the limits of what can be folded into a single rocket fairing. Future observatories, intended to observe distant galaxies, study exoplanets, or detect gravitational waves, may require mirror arrays tens or even hundreds of meters wide. Assembling such observatories in space, with individually launched mirror segments and support structures, could drastically improve their capabilities and sensitivity. Segmented mirror technology and precision robotic alignment will be key enablers of these next-generation observatories. Space-based solar power is another compelling use case for orbital assembly. Massive solar collectors placed in geostationary orbit could harvest sunlight 24/7 and beam energy to Earth using microwave or laser transmission. These systems would require enormous surface areas and precise positioning to maintain alignment with ground receivers. The scale of such installations makes them impractical to launch fully assembled, but ideal candidates for orbital construction. Modular panels, trusses, and power transmission units could be sent into orbit separately and pieced together robotically to form vast energy-harvesting arrays. Human habitation and deep space exploration missions also benefit from orbital assembly. Long-duration missions to Mars or lunar bases may require spacecraft that are too large to launch in one piece. Assembling these vehicles in Earth orbit allows for robust, customizable configurations with radiation shielding, artificial gravity sections, and redundant systems. In addition, space stations or transfer vehicles can be serviced, upgraded, or reconfigured as needed. Habitats could include rotating modules to simulate gravity, modular greenhouses for food production, and repair bays for incoming spacecraft. Artificial gravity structures present a unique challenge and opportunity for orbital assembly. Large rotating habitats could mitigate the long-term health effects of microgravity by generating centrifugal force. Constructing these spinning structures in orbit would require precision engineering, dynamic balancing, and robust attachment mechanisms to withstand rotational stresses. Once operational, such habitats could support long-term human missions in Earth orbit, around the Moon, or en route to Mars. To support assembly operations, a network of logistics platforms, autonomous transport vehicles, and orbital tugs is essential. These assets can deliver components from various launch providers, move them to assembly sites, and position finished structures into operational orbits. Companies are already working on space tugs and orbital transfer vehicles to support this future infrastructure. Combined with orbital depots for fuel and resources, a self-sustaining assembly network becomes feasible. International collaboration and policy development are also critical. Just as the ISS required coordination between multiple space agencies, future orbital assembly projects will likely involve global partnerships. Standardized interfaces, docking mechanisms, and protocols are needed to ensure compatibility across systems. Agencies like NASA, ESA, and JAXA are already working with industry partners to define these standards. The legal and regulatory framework must evolve to accommodate construction rights, debris mitigation responsibilities, and cooperative governance of shared orbital infrastructure. Safety remains a paramount concern. Assembling large structures in orbit introduces risks of collision, structural failure, or component loss. Robotics must be fault-tolerant and capable of operating in various lighting conditions, including full sunlight and deep shadow. Emergency procedures, remote diagnostics, and fail-safe designs must be integrated into every system. In human-rated environments, pressurization, life support, and shielding must meet the highest safety standards. Continuous monitoring and real-time communication with Earth will help mitigate these risks. Orbital debris poses an additional challenge. Construction activities generate debris from discarded packaging, fasteners, or damaged components. Procedures must be in place to capture or deorbit this material to prevent it from becoming hazardous to other spacecraft. In some cases, debris could be recycled into new construction material using in-space manufacturing techniques. Robotic systems might be equipped with tools to capture and repurpose debris into useful structures. Public and private investment in orbital assembly is growing. Companies like Redwire, Maxar, and Sierra Space are developing modular systems for commercial space stations, industrial platforms, and scientific missions. NASA's Artemis program and Gateway lunar platform envision modular assembly around the Moon to support lunar surface operations. China and Russia are also planning modular space stations that can expand over time. Commercial entities are exploring the construction of space hotels, orbital factories, and observatories as part of a broader space economy. Orbital assembly also opens possibilities for artistic, cultural, and symbolic endeavors in space. Structures built in orbit could include monuments, rotating art installations, or reflectors visible from Earth. These projects would expand the human experience of space beyond science and industry, contributing to our shared cultural heritage. Just as cathedrals, observatories, and space probes have inspired generations, orbital structures could become beacons of human imagination and ambition. As launch costs continue to decrease with the rise of reusable rockets and heavy-lift vehicles, more mass and volume can be delivered to orbit economically. This makes modular and scalable orbital construction even more practical. Advances in propulsion, power systems, and material science will further support this transformation. The interplay between launch systems, on-orbit assembly, and servicing capabilities will shape the architecture of future space missions. Training and education are vital to support this shift. Engineers, technicians, and operators will need new skills in robotic operations, space systems integration, autonomous systems, and orbital mechanics. Academic institutions and space agencies must adapt curricula to address the needs of orbital construction. Simulations, test beds, and on-Earth mock-ups will help train teams and validate technologies before they are deployed in space. The vision of orbital megastructures, massive rings, platforms, or habitats surrounding Earth, once confined to science fiction, is becoming a technical possibility. These structures could support millions of people, industrial activity, or planetary defense systems. While such projects remain in the distant future, the incremental development of orbital assembly capabilities is laying the groundwork. Step by step, the construction of larger, more complex space systems will shift from conceptual exploration to operational reality. In the coming decades, orbital assembly will redefine how we build, live, and work in space. It will turn orbit into a construction site, a logistics hub, and an arena of technological innovation. The ability to assemble and maintain large space structures will not only expand our reach into the solar system, but also establish space as a permanent domain of human activity and enterprise.